Picture the atom in your mind right now. Go ahead, visualize it. You're probably seeing a central sphere, solid, definite, with tiny objects tracing neat elliptical paths around it, like miniature planets orbiting a sun. Clean geometry, predictable trajectories, something you could sketch on a napkin in 30 seconds. That mental image has been drilled into your consciousness since elementary school. It's decorating science classroom posters. It's the logo for atomic energy. Museums suspend these little planetary models from their ceilings on fishing line, proudly displaying humanity's understanding of matter's fundamental structure. Except there's a catastrophic problem with that image. It's not merely oversimplified or incomplete. It's devastatingly, comprehensively wrong. Not close enough for practical purposes, wrong. Not approximately correct at this scale, wrong. Fundamentally, completely, irreconcilably wrong in ways that should make you question whether anything else you absorbed in formal education was accurate. The atom is nothing like a microscopic solar system. Electrons aren't miniature celestial bodies, and if you attempt to comprehend atomic behavior using that planetary model, you won't just get confused. You'll be asking questions that literally cannot be answered because the questions themselves emerge from a false premise. So let me reveal what's genuinely happening inside an atom. Fair warning, you're going to hate this because the actual reality is so profoundly bizarre, so aggressively counterintuitive that your brain will resist accepting it at every turn. Let's begin with hydrogen, the simplest atom in existence. One proton, one electron. That's the complete inventory. Hydrogen is everyone's favorite teaching example precisely because it seems elementary. You imagine the proton as a tiny sphere, maybe 10 to the negative 15 meters in diameter, with the electron floating somewhere out there, roughly 10 to the negative 10 meters distant, tracing some kind of orbital path. First fundamental question, where exactly is the electron right now? Your instinct says, well, it's currently positioned over on the left side of the atom following its circular trajectory. Wrong. Completely wrong. The electron is not over there. The electron doesn't possess a definite position, not because our measurement instruments lack precision, not because we haven't invented sufficiently advanced detection technology, because the electron itself fundamentally doesn't possess a specific position until the instant you measure it. This isn't philosophical interpretation or scientific opinion. This is what the mathematical framework explicitly states. This is what experimental verification demonstrates repeatedly across decades. The electron exists in what we term a superposition state. It's not here or there. It's genuinely here and there, simultaneously present in multiple locations at once. The electron manifests as a cloud of probabilities surrounding the nucleus. Now you're thinking, all right, fine, it's a probability cloud. So the electron is distributed throughout a region of space like fog in a valley. No, that's still incorrect. The electron is not spread out or diluted across space. The electron remains a point particle when you detect it. But before detection, it doesn't possess a location property. What's distributed throughout space is the probability of discovering it in various locations. There's a mathematical function called the wave function that calculates where you're likely to detect the electron if you perform a measurement. In certain regions, the wave function has large values, high probability. In other regions, small values, low probability. In some regions, it's exactly zero. You will never, under any circumstances, find the electron there. But here's where your intuition completely collapses. Before you perform a measurement, the electron isn't secretly hiding in one of those high probability regions. It's not concealed over there while you simply lack information about its whereabouts. It genuinely, fundamentally doesn't have a location. The wave function isn't describing where the electron is. The wave function is the electron. That's the complete description. There's nothing additional. Now let's discuss orbits, because this is where the solar system analogy catastrophically fails. You envision the electron circling the nucleus along a well-defined path, around and around like a race car on a track. Maybe it's traveling at high velocity, maybe slower, but it's definitely traveling somewhere following some trajectory. Wrong again. First problem, if an electron were genuinely orbiting that way, it would be constantly accelerating. Any object moving in a circular path is accelerating even if its speed remains constant, because its direction is continuously changing. And accelerating charged particles radiate electromagnetic energy. They emit photons. That's fundamental electromagnetism. Observed, measured, verified. So if the electron were actually orbiting, it would be constantly hemorrhaging energy, radiating it away as light. And as it loses energy, the orbital radius would shrink. The electron would spiral inward, closer and closer to the nucleus, faster and faster, until collision. It crashes into the proton and the atom implodes. How long would this catastrophic collapse take? Do the calculation yourself. It takes approximately 10 to the negative 11 seconds, 100 trillionth of a second. Every atom in the observable universe should collapse instantaneously. Obviously, that doesn't happen. Atoms are stable, they persist. So the electron cannot be orbiting in any classical sense. Okay, you respond, maybe it's not orbiting in a circle, maybe it's just stationary, held in position by electromagnetic attraction to the nucleus. Also wrong, because if the electron was sitting perfectly still, we would know both its position and its momentum with absolute precision. Position, right there. Momentum, exactly zero. And quantum mechanics explicitly forbids knowing both of those properties precisely at the same time. That's the Heisenberg uncertainty principle. It's not a limitation of measurement technology. It's a fundamental constraint built into the fabric of reality. If you attempt to determine the electron's position precisely, its momentum becomes fundamentally uncertain. If you attempt to determine its momentum precisely, its position becomes fundamentally uncertain. You cannot have both simultaneously. So the electron is neither orbiting nor sitting still. What is it doing? It's not doing anything. It simply exists. It exists as a wave function, a mathematical description of probability distributions. And that wave function has certain allowed shapes and energies. We call these shapes orbitals. An orbital is not a path, it's not a trajectory, it's a region of space where the electron is likely to be found, described mathematically by the wave function. The simplest orbital, hydrogen's ground state, is spherically symmetric. The probability density is highest directly at the nucleus and decreases gradually as you move outward. There's no orbit, no path, no trajectory, just a fuzzy cloud of might be here. Higher energy orbitals have increasingly bizarre shapes. Some resemble dumbbells. Some look like donuts. Some have multiple lobes protruding in different directions. These aren't physical objects you could touch or photograph. They're probability distributions, maps showing where you might find the electron if you decide to look. And here's the genuinely disturbing part. The electron doesn't gradually transition from one orbital to another. It doesn't smoothly slide from the ground state to an excited state. It jumps instantaneously. We call this a quantum leap. One moment the electron's wave function has the shape of the lower orbital. The next moment it has the shape of the higher orbital. There's no intermediate state, no smooth transition. It doesn't travel through the space separating the two orbitals. It just jumps. How does this happen? We don't know. The mathematics describes it perfectly. Experimental results confirm it repeatedly. But there's no mechanism, no explanation for how the electron gets from here to there without passing through the middle. It simply does. Now let's discuss what the electron actually is, because this is where things become genuinely disturbing. You conceptualize the electron as a tiny sphere, a miniature ball with some mass and some electric charge. Maybe it's incredibly small, but it's still an object, a thing, a particle you could point to. Except experimental evidence demonstrates that the electron also behaves like a wave. It can interfere with itself. It can diffract around obstacles. It can spread out and recombine all the characteristic behaviors of waves. So which is it? Particle or wave? Neither. The electron is not a particle, it's not a wave, it's a quantum object. Something that has no classical analogy whatsoever. Something that exhibits particle-like behavior in certain experiments and wave-like behavior in others, but is fundamentally neither one. When you're not observing it, it's described by a wave function. That wave function evolves smoothly, spreading out, interfering with itself, doing everything waves do. But when you measure the electron, when you actually detect it, you always find a localized particle, a dot on a detector screen, a click in a counter, never a smeared out wave. The act of measurement collapses the wave function. The distributed probability cloud instantaneously becomes a definite outcome. Here, not there. One location, localized. And nobody knows how this happens. Nobody knows what qualifies as a measurement. Nobody knows where the wave function goes when it collapses. This is called the measurement problem. And it's been frustrating physicists for nearly a century. There are interpretations, many worlds, pilot wave theory, objective collapse, but they're interpretations, not solutions. The mathematics works flawlessly. The predictions match experimental results, but we don't have a clear picture of what's actually occurring. Let's make this worse. Let's add more electrons. Helium has 2 electrons. Lithium has 3. Carbon has 6. Iron has 26. These electrons are all existing simultaneously as wave functions around the nucleus. But here's the critical point. The electrons are identical, absolutely, perfectly, fundamentally identical. There's no method to distinguish them, not because they appear similar, not because they are very much alike, because they are the same. Electron number 1 and electron number 2 are not 2 separate entities that happen to share the same properties. They're the same entity appearing in 2 locations. This has profound consequences. If you swap 2 electrons, the wave function of the entire system changes sign. It picks up a negative factor. This isn't a minor detail. This is fundamental. It's called the Pauli exclusion principle. And it's the reason matter is solid. The reason you don't fall through the floor. The reason atoms have structure and chemistry functions and life exists. No 2 electrons can occupy the identical quantum state. If one electron is in a particular orbital with a particular spin orientation, no other electron can be in that exact same state. They have to stack up, filling different orbitals, constructing the structure we call the periodic table. Without this rule, all electrons would collapse into the lowest energy state. Every atom would be chemically identical. There would be no complexity, no molecular diversity, no chemistry, no biological structures, But why? Why does swapping identical particles change the sign of the wave function? We don't know. It's simply the rule we discovered. The mathematics works. Experimental results agree. But there's no deeper explanation available. Now let's discuss the nucleus, because you probably assume that part is straightforward. A collection of protons and neutrons packed together. Little spheres stuck to each other like magnets. Wrong again. Protons and neutrons are not fundamental particles. They're composed of quarks. 3 quarks each, up quarks and down quarks, held together by the strong nuclear force mediated by particles called gluons. But the quarks don't sit stationary inside the proton. They're quantum fields fluctuating, interacting, constantly exchanging gluons. The proton doesn't contain 3 quarks. The way a container holds marbles, the proton is a bound state of the quark field, a stable pattern of oscillation in a quantum field. And here's the truly bizarre part. Most of the proton's mass doesn't originate from the quarks themselves. Quarks are nearly massless. Most of the mass comes from the energy of the gluon field holding the quarks together. Energy equals mass. So when you ask what's inside a fermion, the answer is energy. Bound field energy, not stuff, not particles. Energy arranged in a stable pattern. And the protons and neutrons in the nucleus, they're held together by the residual strong force. They're not touching. They're not glued together. They're trapped in a potential well created by the exchange of particles called pions. But pions are also made of quarks. It's quantum fields, all the way down. So let's step back and ask the question again. What's really inside an atom? Not particles, not little spheres, not orbits, not stuff. What's inside an atom is fields, quantum fields. The electron field, the quark field, the gluon field, the electromagnetic field. These fields fill all of space. They're everywhere, always. When we say there's an electron in an atom, we mean the electron field has an excitation localized near the nucleus. The atom is not a thing. It's a pattern, a stable configuration of field excitations held together by forces that are themselves carried by other field excitations. There are no solid objects at the foundation. There's no stuff. There's only fields. And the fields are just mathematical objects that assign numbers to every point in space and time. Numbers that evolve according to differential equations. Numbers that sometimes produce localized excitations we call particles. You don't like this. I can tell. You want there to be something tangible at the bottom, something solid, something you can point to and declare that that's what it's made of. But there isn't. There's just mathematics. Equations, symmetries, conservation laws, and somehow miraculously that mathematics produces the appearance of solid objects, tables, chairs, your own body. All of it is patterns in quantum fields held together by forces stabilized by exclusion principles, flickering in and out of existence trillions of times per second. Here's another thing that will bother you. People say the atom is mostly empty space. You've heard this countless times, but that's wrong too, because empty space doesn't mean nothing. The quantum fields are still there. Virtual particles are popping in and out of existence. The vacuum is seething with activity, and the electron's wave function fills the entire atomic volume. The electron is there in the sense that its probability amplitude is non-zero throughout the atom. When you push on a table, you're not feeling particles colliding. You're feeling electromagnetic repulsion between electron clouds, field configurations, resisting overlap, the Pauli exclusion principle preventing electrons from occupying the same state. It feels solid because the forces are strong, but there's no actual contact, no touching, just fields pushing against fields. Now let's discuss what happens when you try to look inside the atom. You can't use visible light because the wavelength of visible light is larger than the atom. You need something with a shorter wavelength, which means higher energy. But here's the fundamental problem. The moment you use high energy probes to examine the electron, you disturb it. You knock it out of its state. You change what you're trying to measure. This isn't a technical limitation that better instruments might overcome. It's fundamental. To see something small, you need short wavelength light. Short wavelength means high energy. High energy means large disturbance. You cannot avoid it. The act of measurement inherently changes the system. There's no such thing as passive observation at the quantum level. This is why we cannot say where the electron is before we measure it. Not because it's hiding somewhere, but because the property of being in a definite location doesn't exist until we perform a measurement that creates that property. Before measurement, the electron is described by a wave function, a superposition of possibilities. After measurement, the electron is in a definite state, one of those possibilities actualized. The measurement doesn't reveal a pre-existing reality. It creates a definite reality from a fuzzy one. So what's really inside an atom? Not little spheres, not orbits, not stuff, not even particles in the way you conceptualize particles. What's inside an atom is a mathematical structure, a wave function, a solution to the Schrödinger equation, a pattern of probability amplitudes that tells you what you'll find if you look, but doesn't describe a definite reality when you're not looking. The atom is a quantum system, and quantum systems don't behave like anything in your everyday experience. They exist in superpositions. They have properties that are fundamentally uncertain. They defy visualization. You cannot picture what's inside an atom because there's nothing to picture. The wave function is not a physical wave propagating through space. It's a function in an abstract mathematical space called Hilbert space. It's a list of complex numbers that encode probabilities. It's information, not substance. And yet from this abstract mathematical structure, the entire physical world emerges. Chemistry, biology, consciousness. All of it constructed from patterns in quantum fields, governed by equations, following rules that make no intuitive sense, but work with astonishing precision. This is what's really inside an atom. Not particles, not stuff, but mathematics. Pure, abstract, beautiful, incomprehensible mathematics. And if that doesn't satisfy you, if you still want there to be something more, something solid and real at the foundation of it all, well, I'm sorry, but the universe doesn't care what you want. It is what it is. And what it is turns out to be far stranger than you ever imagined.